Sorry. Okay, so we're going into August now. And this week is on wave optics. We saw a few weeks ago that light is a wave. In fact, light is two waves. It's an electric field wave and a magnetic field wave, which go together. Last week was about the interaction between light and matter, and that led to geometrical optics, reflection and refraction. Now this week is about the interaction between light and light, and that will give wave optics. If we have two light waves and they're overlapping, they interact with each other. They combine. That's called the superposition principle. When you add waves, you can get constructive interference or destructive interference. So first of all, we'll have some examples of interference. For example, thin films or Newton's rings. And then we'll combine interference with diffraction. Diffraction is what happens when a wave passes through an opening. And that'll give, as examples, Young's experiment, two-slit interference, and gratings. So let's go over some problems from the homework assignment. This first problem is a problem about Newton's rings. A beam of light falls normally on a plano-convex lens. So here's the incoming light, and it hits this lens. The top surface of the lens is planar. The bottom surface of the lens is spherical. And the lens rests on a plane glass surface. So when the light comes in, part of it will go into the glass, reflect off the spherical surface, and come back out. But part of the light will go through the glass and into the air, reflect off the flat surface, back into the glass, through the glass, and then out, and you'll have two beams of light overlapping, and they will interfere. And what happens is you get rings, regions of bright light and regions of darkness. And that's the interference of these two waves. Now, the radius of curvature of the surface is given, and the problem is to calculate the radius of a dark ring, the eighth dark ring, let's say. Not counting the dark ring in the center, we'd come out here 1, 2, 3, 4, 5, 6, 7, 8. What's the radius of this ring? And this was something that was discovered by Isaac Newton and not really understood by him, which is a little unusual. Well, maybe he did understand, but he did not understand the wave theory of light. So his explanation was not really correct. Whoops, what happened? All right, so you see the two beams of light travel different distances. Now, we're really going to consider incident light perpendicular to the flat surface of the lens. That's not what the diagram shows, but that's the simplest case. So the incoming light is perpendicular to the flat surface, and then the outgoing rays will also both be perpendicular and interfering. So there's a path difference. And as it says in this picture, there's an air gap and there's an interference of the outgoing rays that depends on the difference in the path length. So the difference in the path length will be, well, it'll be this little distance right here, times 2, because the light comes in, one ray goes out into the air and then bounces off the plane surface and then goes back into the glass. So it's actually 2 times this difference. The length to the lower surface is r. That's the radius of curvature of the spherical surface, minus the square root of r squared minus x squared, where x is this distance. So x will be the radius of the ring. So it's not 2r, it's 2 times r minus the square root of r squared minus x squared. You know, the distance to the top surface of the lower sheet of glass is r. The distance to this surface is the square root of r squared minus x squared, because the formula for a circle or a sphere is x squared plus y squared equals r squared. So delta y is the square root of r squared minus x squared. Now, we'll assume that r is very large. So in other words, we'll assume that the spherical surface differs from a plane by a small amount. So in other words, x is small compared to r. And then if we use the Taylor series expansion for the square root of r squared minus x squared, that's r minus x squared over 2r. We'll have r minus r, that's 0. Minus minus is plus x squared over 2r times 2. So x squared over r. So the path difference is x squared over r. Now the optical phase difference is k, the wave vector, which is just 2 pi over lambda, times the path difference. Remember, the wave goes like cosine kx minus omega t. Well, no, k times s minus omega t. So k delta s is 2 pi over lambda delta s. So that's the phase difference. If delta s is lambda, one wavelength, then the phase difference is 2 pi. That's 360 degrees. So 2 pi will be in radians. But then there's an extra amount of phase difference, because reflection from a dense material into a less dense material, like reflection from glass into air, and reflection from a less dense material to a more dense material, that would be like from air into glass, differ by 180 degrees. There's a 180 degree phase change for the reflection of a wave coming from a more dense material into a less dense material, or coming from a less dense material onto a more dense material. So there's an extra phase change of 180 degrees, I have to put it into radians, so that's pi radians. We put in delta S here as x squared over r, factor out 2 pi, we have x squared over r lambda minus a half. So that's the phase difference. Now, if the phase difference is an integer number, an integer power of 2 pi, then you get a bright ring. You get constructive interference. So constructive interference means the phase difference is 2 pi, 4 pi, 6 pi. In other words, it's an integer multiple of a whole wavelength. A whole wavelength in terms of the phase is 2 pi radians. So if delta phi is 2 pi m or 4 pi m or 6 pi m, the two outgoing waves are completely in phase. They will undergo constructive interference. So if I solve this equation where delta phi is 2 pi m, I find that x, the radius, is r times m plus a half. The half comes from this extra phase change of 180 degrees times lambda, where lambda is the wavelength. So those are the radii of the bright rings. Now, the problem asks for the dark ring, the 8th dark ring. But you can see from the picture, or from the geometry here, the dark rings are just in between the bright rings. So the dark rings will correspond to, now, this is the next problem. This is two-slit interference. This is a combination of interference and diffraction. When light goes through an opening, it spreads out in all directions. You know, we're used to the idea that light in a uniform medium just travels in a straight line. But when light goes through an opening in an opaque screen, it doesn't just travel in a straight line. It spreads out in all directions on the other side of the opaque screen. And that's called diffraction. So if we had two thin slits and light incident on that, we'll have two sources of light on the other side, spreading out from the two openings. And where they overlap, you have constructive or destructive interference. So the formula is obtained by considering two sources of light, and the light that hits this screen at some distance L away from the two slits. They have two different lengths. So from the upper slit, we have a length L, and from the lower slit, we have a length L prime. And constructive interference will occur if the difference in the path lengths is an integer number of wavelengths, because this will be reaching, let's say this is reaching a crest of the wave, and let's say this is one wavelength longer, then this ray will also be reaching the crest of the wave. So the two crests will be occurring at the same point Y. There'll be constructive interference at Y. The amplitude of the combined wave will be 2 times the amplitude of either wave. So if L prime minus L is M lambda, where M is an integer, then you'll have constructive interference on the screen, on the projection screen. So there's a bit of trigonometry that we have to go through to analyze the difference in path lengths in terms of the given quantities. What's given? Well, the wavelength, the distance between the two slits. So this one is at d over 2, this one's at minus d over 2, so the distance is d, and the distance to the screen. Now, by a little bit of trigonometry, if we look at this right triangle, we see the tangent of this angle. Let's look at this angle. We can call that theta for L. The tangent of theta is this distance, y minus d over 2, divided by this length, L. So L times the, so here it is, L times the tangent of theta is y minus d over 2. Now we can also look at that triangle and say the sine of theta will be y minus d over 2, the opposite of theta, divided by the hypotenuse, which is L. So L times the sine of theta is also y minus d over 2. And similarly, for this lower ray, we could call this angle theta prime, goes along with the length L prime. L sine theta prime is y plus d over 2, because the opposite to that angle is y plus the extra d over 2. So L sine theta, sorry, L tangent theta prime is y plus d over 2. And L prime sine theta prime, so that's y minus d over 2 divided by the hypotenuse times L. That's L sine theta prime. That's this one. L prime, that's L prime. That's the hypotenuse for the lower triangle. Sine theta prime. Now we want L prime minus L. Should be m lambda. So L prime is L tangent divided by sine for theta prime. And L is L tangent theta over sine theta. So we'll use a little bit of trigonometry here. Tangent alpha over sine alpha is the square root of 1 plus tangent squared alpha. So the condition for constructive interference is m lambda is capital L, 1 plus tangent squared theta prime, minus capital L, square root of 1 plus tangent squared of theta. Now again, the angles here will all be very small. So I can approximate tangent theta prime as a small number. The square root of 1 plus epsilon is 1 plus a half epsilon. And the square root of 1 plus tangent squared theta is 1 plus a half tangent squared theta. So the ones will cancel, and I'll have L times a half tangent squared theta prime minus L times a half tangent squared theta. And tangent theta, well, tangent theta prime is y plus d over 2 squared. We'll have that. And then minus y minus d over 2 squared. Y squared minus y squared is 0. D over 2 squared minus d over 2 squared is 0. But I'll have the cross terms. 2 times y times d over 2 is y times d minus y times d. So when I combine them, that'll be 2y over d. So I'll have L over 2, 2y over d, 2y times d. So that'll be y times d over L. So that's the condition for constructive interference. Y should be L over D times M lambda, where M's an integer. Now, in this case, M can be 0, plus minus 1, plus minus 2, plus minus 3, and so on. So you get this pattern of bright fringes and dark fringes. So that's the equation that you'll find in the book for constructive interference in two-slit interference experiment, Young's experiment. So that's equation 34.8. I didn't really have to go through this long derivation to solve the problem. I could just start at this point, take this out of the book. Now I want to know what is the distance to the nearest bright fringe. The center bright spot is M equals 0. The nearest bright fringe will be M equal plus or minus 1. So the distance from the center bright fringe to the nearest one will just be lambda L over 2, M equal 1. If white light illuminates a soap bubble, we see rainbow colors. So here's white light, a photograph of white light reflecting from soap bubbles. And you see how you see the colors of the rainbow. The reason is because white light is a mixture of all the colors. So white light is a superposition of all different wavelengths. At certain angles, each wavelength will undergo constructive interference. So if you're looking at that angle, you'll see that color, because there'll be constructive interference for that wavelength and not for the other wavelengths. So at some angles, you'll see red. At other angles, you'll see blue. At other angles, you'll see green. Now we want to consider this wavelength, 460 nanometers, which would be blue or violet. And we can, for the small region where the reflection is taking place, we can treat the soap bubble as a flat surface. So we just need to analyze light incident normally on a planar soap film. So here's the incoming light. It reflects off the upper surface, or the, here's the film. It's horizontal, gravity is downward. Here's the film. Above the film, we have reflection from the top surface. Some of the light will be transmitted into the film with a bit of refraction, and then some of that light will reflect from the lower surface of the film. So it's kind of like the case of Newton's rings. We have light reflected from two surfaces. And so the outgoing light, these are just the rays, but the waves are perpendicular to the rays. Well, these waves, depending on the angle, will overlap. And they may, if they overlap in just the right way, you may have constructive interference or destructive interference. Now, this picture is more general than the problem we're going to do. The problem we're going to do is light incident normally. So not like this. The light is going to come in perpendicular to the surface. And then some of it will reflect from the upper surface. Some of it will reflect from the other upper surface and come back out in the same direction. Some of it will reflect from the lower surface and come back out in the same direction. And then those two waves will be overlapping, they will interfere. Depending on the thickness of the surface, in the original diagram, it was called D, but in the problem, it's called T, or at least in the analysis, it's called T. At the correct surface, at the correct thickness, these two outgoing waves will be interfering constructively. And so you'll get bright reflection in that direction. Well, bright reflection perpendicular for that thickness, and not for other thicknesses, and not for other wavelengths. So this is an example of thin film interference, where the film is the soap film. And the constructive interference is given by the same equation as for Newton's rings. The path difference has to be an integer multiple of the number of the wavelength plus an extra half a wavelength because of the change in phase when light reflects from a less dense material like air onto a more dense material like water. There can be a phase change relative to the case where light reflects from a more dense material like water onto a surface with a less dense material like air. So I guess the phase change occurs here. There's 180 degrees phase change here relative to this reflection. So the condition for constructive interference is not an integer number of wavelengths, but an integer number of wavelengths plus an extra half a wavelength to give that extra 180 degree change in phase. So delta S, m plus a half lambda, m can be 0, 1, 2, 3, and so on. Now it asks about second order constructive interference. Well, second order constructive interference means m equals 1, because the first order interference is m equals 0. The first integer would be m equals 0. Second integer would be m equals 1. So second order constructive interference means m equals 1. Now that's the condition for constructive interference. What is the path difference, delta S? Well, again, for normal incidence and then normal reflection, the path difference is 2 times the thickness, because the light has to go through the top surface, reflect from the bottom surface, back out through the top surface. So that's 2 times the thickness. So the condition for constructive interference is 2t is m plus a half lambda. So t is a half m plus a half lambda. And again, that's the equation in this section of the chapter on thin film interference. So we don't have to go through all this analysis. You just read the textbook, the section on thin film interference, and pick out the formula for the thickness for second order constructive interference. Oh, second order constructive interference will be m equals 1. So thickness of 3/4 lambda. The example that's given in the book is first order constructive interference, which is m equals 0, which is thickness 1/4 lambda. But you see, in order to get the kind of constructive interference, you have to have a thickness which is something comparable to the wavelength of the light. Now, what's lambda here? The lambda is the wavelength of the light when it goes through the water. So lambda is the wavelength in the film. But the light here is 460 nanometers in the air. So this wavelength is what's given in the problem as lambda. And this wavelength is lambda in the film. So you have to be careful. Lambda in the film is not equal to lambda in the air. The speed of light is slower in the water than in the air. Here's another example of diffraction. Whenever a wave, not just light, but any wave, could be a water wave or even a sound wave, whenever a wave goes through an opening, it spreads out in all directions. And there may be interference of waves coming from different directions. So here is diffraction through a disk or through a circular hole. So this is the diffraction of light coming through a circular hole. For example, coming through a telescope. Suppose we had two sources of light. And our telescope, here's our telescope. Well, here's our telescope. Right down here is our telescope. Here's our telescope. And suppose I had not one source of light, but two sources of light close together. So suppose I had two sources of light. What would I see down here? Well, I'd see two stars, or maybe two galaxies. But if they're very close together, could I tell them apart? Now, if the light was just a point, then there wouldn't be any overlap. But because the light is a little bit spread out, well, even if the light was a point, I would have diffraction as it comes through the front of the telescope. So here's the opening. This is where the diffraction occurs. There's diffraction as the light goes through the front of the telescope. Whenever waves go through an opening, they spread out. And so the two images of these two stars would produce two diffraction patterns. Now, if the stars are far enough apart, I would see, I really ought to show these stars as little points. A star is just a point of light, really. So I have two little points of light, but what I see in the telescope is two regions of light forming a diffraction pattern. Now, if the two stars are far enough apart, I could tell them apart in spite of the fact that they are not point-like in the telescope. But if they're closer together, if they're very close together, the two diffraction patterns would overlap, and I wouldn't be able to tell if that's one source or two sources. And there's a kind of characteristic distance where I can just barely tell that there's a difference. And that's called the Rayleigh Criterion. If the angle between the two sources is 1.22 lambda over d, What's D? I shouldn't have put D here. This is D, the size of the telescope opening where the diffraction occurs. The diffraction occurs here if the angle is equal to 1.22 lambda over D, then I'm in this condition where I can just barely tell the two points. You know, if the angle is anything smaller than that, it would look like this. I couldn't tell that there were actually 2 points there. If the angle were larger than that, then I'd get this and I could tell there were two sources there. But the kind of in-between case, the critical case, is where the angle is 1.22 lambda over D, where D is the opening of the place where diffraction occurs in front of the telescope. Now, okay, so part A is, what's the angular resolution? Well, this is the angular resolution, 1.22 lambda over D. And now, what's the corresponding linear resolution? Well, this is the linear resolution. The linear resolution is this distance D. Now, by trigonometry, theta is D over R, where R is the distance from the telescope to the source, to the stars. So this is R. This is the 2.4 billion light years. So this is 2.4 giga per billion light years. A light year is the distance that light travels in a year. So it's the speed of light, 3 times 10 to the 8th meters per second, times the number of seconds in a year, 3.15 times 10 to the 7 seconds. So a light year is 3 times 10 to the 8th times approximately 3 times 10 to the 7th. So a light year is approximately 9 times 10 to the 15 meters. This is 2.4 of those light years. And so the linear resolution will just be R times theta min. So in part B, we're supposed to calculate the linear resolution. Well, what I'm calling the linear resolution is D. So D would be theta R. Theta, I calculate from this condition. So part A determines theta, part B determines D. Now that's if I add 2 sources of light. But in this experiment, there's only one source of light. It's the quasar. It's this quasar whose name is 3C273. I could talk about 2 sources of light, or I could talk about light from one side of the quasar and light from the other side of the quasar. Can I tell the difference between the 2 sides of the quasar? Well, it would require D equals R, the size, in other words, the diameter of the quasar would have to be R times theta min, 1.22 lambda R over D. D is this 2.4 gigalight years. Lambda is visible light. So we just take 589 nanometers. That's kind of typical center of the visible light spectrum. And D is the diameter of the telescope. In this case, D is 200 inches. That's one of the biggest reflecting telescopes available at that time. Okay, now the question, part C, is to compare that size, that linear resolution, where you could tell the size or the diameter of this object, to the diameter of the Andromeda galaxy. Here's a picture of a transmission grating where you have light incident on an opaque slide with a large number of grooves cut in the slide, or slits cut in the slide. It's like an opaque screen with end slits. We considered before the example of an opaque screen with 2 slits. Well, this is an opaque screen with end slits. And the light coming through all those slits undergoes diffraction, and they all interfere. So in some directions, some angle theta, there'll be constructive interference, and we'll get a bright region of light. If we projected the light onto a screen over here, there would be bright regions where there's constructive interference. Now, this is actually an example of a reflection grating, but a reflection grating is really just about the same as a transmission grating. It's just that the light doesn't come through the grating. It reflects from the surface of the grating. So the light in a reflection grating would be coming in this direction and reflecting from grooves in the surface, little cutout regions in the surface. And so each little groove acts as a point of, as a source, just as in the transmission grating, each slit acts as a separate source. And so in either case, the angle for constructive interference would be given by the same. It's the grating equation. D sine theta is the difference. You know, if I look at D sine theta, it's this distance here. It's the path difference between 2 neighboring slits or 2 neighboring grooves in a reflection grating. If that path difference is an integer number of wavelengths, then out here, where these 2 rays collect, they will be undergoing constructive interference. So that's the grating equation. It's like the equation for two-slit interference. Where was it? Not quite. It's not exactly the same as two-slit interference, but it's similar. Now, it says that there are n lines per centimeter, and part A is for 10,000. So if there are 10,000 lines per centimeter, that means the distance between 2 lines is 10 to the minus 4 centimeters. There's 1 line each 10 to the minus 4 centimeters. So the 10 to the 4th lines in 1 centimeter. And then what's the angle of the first order diffraction image, the first order bright region? Well, it'll be given by m equals 1. So theta will be the arc sine m lambda over d. And this d is 10 to the minus 4. So it'll be lambda, which I guess is this blue color or violet color, 466 nanometers divided by 10 to the minus 4 centimeters is 10 to the minus 6 meters. So that'll be 466 times 10 to the minus 3, 0.466 radians. Part B says, what's the maximum value of n such that a second order image will occur? So that would correspond to m equals 2. So you would get a bright region at sine theta equals 2 lambda over d. Where theta is arc sine 2 lambda over d. Now this equation does not have a solution if 2 lambda over d is greater than 1. It's the sine of theta is 2 lambda over d. Well, the sine of any angle is less than 1. So the only solution is possible if 2 lambda over d is less than 1. There's no such thing as the arc sine of a number greater than 1. So 2 lambda over d has to be less than 1. That is to say, d has to be greater than 2 lambda. The distance between the slits has to be large enough to see the second order image, the second order diffraction fringe. Now this problem is also considered in the book, where the example is the surface of a CD or the surface of a DVD. There's a section of the book on interference of light reflected from the surface of a CD. And you know, if you look at the surface of a CD or a DVD, white light reflecting from that surface will show the colors of the rainbow, because there will be constructive interference in certain angles, and the angle depends on lambda. All right, so in this problem, in part B, the question is, what's D? No, the question is, what's N? Whoops, I didn't mean to stop that. The question is, what's N? Remember, D and N are related by this equation.